Good morning, everybody. My name is Elena Walker, and I'm the current president of EUCA, and I'm here with enormous pleasure to introduce Marian Kangarpour, who's the 2024 European Control Award recipient. Let me read the motivation: for fundamental contributions to stochastic control and multi-agent learning and control. Let me give you some information about the European Control Award. The European Control Award was established 10 years ago in 2014, and is meant to recognize outstanding contribution by a young researcher in the area of systems and control, and is sponsored by EUCA, and part of the award is a speech that is delivered during the European Control Conference. Let me give also some information about the awardee. Marian Kangarpour took her PhD at the University of California in Berkeley. She served as a faculty at ETH Zurich and UBC, Canada, before joining EPFL, where she is currently a tenure-track assistant professor. She is the recipient of the NASA Excellence in Publication Award, of the 2022 IEEE Transaction Control and Network Systems Best Paper Award, and of an ERC starting grant. Her research interests are on safe decision-making and control and uncertainty, game theory and mechanism design, mixed integer and stochastic optimization and control, with applications in the area of intelligent transportation networks, robotics, power grid systems, and healthcare. Before I invite Marian to give the lecture, I would kindly ask you to stay at the end of the lecture, not only in case you have questions, but that depends pretty much on the timing, but also to see that I give her the plaque, I recognize her finally for this very outstanding award. And also, I would also ask to remain for a short presentation from George Rovitaki, who's the General Chair of ECC2025 of the next ECC conference. Marian, please.
Good morning, everyone. It's a great pleasure to receive this distinguished award for my passion, and it's my honor to be here with you and give this lecture this morning. Okay, so we see our control systems evolving from simple single systems in fairly predictable environments to larger-scale interactive subsystems with increasing amount of uncertainties. So these uncertainties could be from our partial knowledge of future, for example, output of weather-based renewable sources of energy, or from decision-making of the subsystems, for example, trajectories of the cars in an intelligent transportation system. They could also be from partial difficulty on modeling a complex system. For example, in robots, collaborating and doing complex tasks such as construction, it's difficult to describe a detailed, high-scale model accurately. And our goal is to develop modeling and control approaches that enable us to have provable performance guarantees for these systems, which are multi-agent, large-scale, nonlinear, highly interactive. And we would like to incorporate real-time data because that's something we have abundantly now to be able to improve the performance. So the stochastic control framework is a modeling framework that allows us to incorporate these uncertainties and interactions. So in a stochastic control system, the state x at time t+1 is a sample from a probability distribution P, which gives a distribution on the next state, conditioned on the state at current time and the input at the current time. And the problem is to design a controller, so as a function pi from the state to the actions, to minimize an expectation of a running stage-wise cost, okay? C. And this cost can be over a finite horizon, or it can be over an infinite horizon, in which case we can do discounting or averaging in order to make sure that the sum is bounded. So the classical approach to solve this problem is dynamic programming. So the dynamic programming approach takes the model, the transition probability, and our objective, and gives us some optimality conditions. And these conditions characterize the optimal function, the policy that solves this control problem. And then we can use this optimality conditions to synthesize a control policy for our system. Over the past 7 decades, there's been a lot of progress in dynamic programming. For example, we can address more general objectives such as safety, reachability, or objectives coming from temporal logic specifications. We have done multi-agent formulation and solution characterization for this problem. And the community has worked on addressing these advances and also developed a lot of approaches to solve these problems tractably. In the picture, for example, you see an application of dynamic programming to safe trajectory planning for aircraft. So here we use the weather forecast and here in the picture you see regions of the sky that have high precipitation, and these are potentials for the storm. And we develop a stochastic model of future evolution of the storms, and then we use DP to plan the aircraft trajectory that maximizes probability of a safe flight from an origin to a destination. So this approach is a solid way to solve this problem, and the community has made a lot of progress, but still it's not scalable. So if in this example, it would be hard to incorporate more than one aircraft. Computational tractability is a limitation. And it's also hard to incorporate real-time data about the system and update our models about the storm or about the aircraft or just the evolution of the environment. Now, in the reinforcement learning approach to stochastic control, we no longer assume we have the model. And the idea is that we optimize this control policy by interacting with the system. So the system is like a black box to us, which we don't know its transition probability kernel. We can apply a policy pi and get a trajectory from the system. And based on these trajectories, we want to update the policy. And RL has seen a lot of successes in board games, chess, Go, in video games, very complex multi-agent decision-making problems. And it's been also advocated for solving safety-aware control systems. But the key challenge to apply RL for safe control is having provable performance guarantees. And in this talk, I'm going to focus on our work towards incorporating performance guarantees in reinforcement learning for safe control systems. So the outline of the talk is we're going to talk about safe learning for a single agent. So I'm going to talk about the constrained reinforcement learning formulation and our log barrier approach. Then we're going to focus on multi-agent learning and control, and I'm going to highlight the challenges compared to a single agent setting and highlight some work on the multi-agent reinforcement learning before I conclude. Okay, so before I get started on safe learning for a single agent control, I want to acknowledge the work by the community on incorporating safety in learning and control. So there are many excellent researchers who have been focusing on these problems from different angles. In the constrained RL setting from the reinforcement learning community, there's works using Lagrangian formulation, constrained policy optimization, and model-based approaches. In the control community, we have been developing the community many approaches because of the importance of this safety, such as learning-based safe model predictive control, data-driven model predictive control with safety guarantees, safely training neural networks, formal methods for reinforcement learning, for verifying reinforcement learning, certificate functions such as Lyapunov or control barrier functions, and also safe Gaussian process learning. This is just to say that we extend on the shoulders of giant, and we're building on these works, and I apologize if I did not include some of the references because many people also from this room are contributing to these problems. Okay, so let's go through the constrained reinforcement learning problem. So here we are in the reinforcement learning where the model is not known anymore. And the approach here is we're going to parameterize the policy. So this function pi now becomes parameterized by a finite dimensional parameter theta. And we're also looking at the stochastic policies here, because in reinforcement learning, when we don't know the model, the policy has to explore the state space. So pi theta is a probability distribution on the next input given the current state. And the objective, as before, is minimize a function, the running sum of the expectation of this cost function, subject to now some constraints. Okay. And the data is our system trajectory. So we apply pi theta k, we observe a trajectory, and now we want to come up with an algorithm that is safe learning, meaning that pi theta k satisfy the constraints at each iteration and converge to the optimal policy. So this is a problem we like to address now. Okay, so let's go about how we're going to look at this problem. So by parameterizing the policy, first of all, we formulate our infinite dimensional search over function spaces to a finite dimensional search. And there are different ways to parameterize a policy. For example, a linear policy is perhaps the most familiar to us. In reinforcement learning, we need policies to be exploring. So we have randomized policies, such as a Gaussian policy, which is pi is a probability distribution with a mean function, phi function of x, parameterized by theta. And this could be a neural network. This phi could be a neural network, and theta are the parameters of the neural network that we are training to solve the RL problem, and a covariance, which can also be parameterized and state dependent. And with this parameterization, our constrained reinforcement learning problem becomes equivalent to a constrained optimization problem in the parameter space. So constrained optimization, of course, is a standard problem that we solve in optimization, but the challenge here is that J and C are unknown because we don't assume we know the model of the system. So we cannot predict the trajectories without a model and compute these expectations. So this is like a black box constrained optimization problem. And now our safe learning is to design a sequence of parameters, theta k, such that these constraints are satisfied at each time, and theta k goes to the optimal policy parameter. So in an optimization framework, if this is our feasible set and theta 0 is our feasible initial condition, we have to figure out how to search the space. And one approach is to look at descent directions along the objective and take step sizes along this descent direction until you go to the optimal solution. There are a couple of challenges in the RL setting, as that J and C are generally highly non-convex, and J and C are unknown. Okay, good. So before going into the detail of how we address this, I'm going to give a high-level overview of how we can address this problem. So the idea of the approach we propose is to design a barrier function to stay inside a feasible set and estimate the gradients to find a descent direction and take a carefully chosen step in the descent direction. Okay. But we have to do all of these when we don't know J and C. And we're going to go through how we do this. OK, so as for the barrier function, we consider a logarithmic barrier of the constraint set. So this function grows to infinity when theta approaches the boundary of the set. So if we start in the set, this function can help us stay in the feasible set. And with this formulation, we can recast our constrained optimization as an unconstrained optimization problem, where J tilde is our new cost and is J of theta minus eta, our parameter that we will tune, and this logarithm of the constraint. OK, now we have an unconstrained optimization problem, and we can imagine a gradient descent approach where theta k plus 1 is equal to the theta k parameter at time k minus our step size gamma k times our gradient direction. And the challenges that we have to answer now, if this algorithm converges, would it converge to the optimal policy parameters of our RL constrained RL problem? How to construct a good estimate of the log barrier gradient without knowing J and C, and how to choose the step size for safety and convergence. And we're going to look at these 3 questions in the next 3 slides. Okay. So the first helping lemma is that the RL problem structure gives us some nice properties of this barrier function. In particular, the stationary points of log barrier are approximately optimal for our objective. So, as mentioned, J and C are highly non-convex. Imagine theta parameterizing some neural network, but this RL problem structure gives us some nice property. So when the gradient of the barrier function goes to 0, we can see from the left-hand side that the parameter theta is near parameter theta star by about factor of eta. So by carefully decreasing eta as we do this procedure, we can hope to converge to the right parameter. So this is an example of such function which could be non-convex. It has several stationary points, but if red here is j of theta star, the cost function evaluated at the optimal parameter, we can bound the suboptimality of these stationary points. So it could be a good idea to use gradient descent on the log barrier, because if gradient descent converges, we are approximately optimal. So the next question is, how do we estimate gradients without knowing the functions? Okay. The gradient of the log barrier in closed form can be written as the gradient of our cost function of the constraint RL minus eta times gradient of the constraint function divided by the constraint function value. And now here we use the data of that system. So we use sample average estimates, but we create sample average estimates of these quantities. So by querying our system, we submit pi theta n times, and we observe n trajectories of the systems. And then we can characterize the number of samples needed such that the barrier gradient estimate that we create is within an accuracy of epsilon with confidence 1 minus delta. And we need these high confidence estimates because we want to have some safety guarantee. So we should be able to control the accuracy of gradient estimation based on sample averages. Okay, now on ensuring safety of the iterates. And here gamma k, we are looking at gamma k, which is the step size of our procedure. And we already replaced the exact gradients with our sample average estimate of the gradients. And in such a gradient descent scheme, gamma k should be sufficiently large to make progress and not get stuck as it's moving, this dynamical system is moving. But it also has to be sufficiently small to keep the iterates safe. And to address both of these objectives, we use our local sample average estimates to create quadratic upper bounds on the constraint and the objective function. So in the picture, you see C hat at a given point theta k is our sample average estimate of the constraint, and we have high probability confidence intervals for this C hat. And we also have confidence intervals for this gradient estimate. And based on this, we can estimate a quadratic function that upper bounds this constraint. And we can use that to then bound our step size so that it's safe with high probability. Similar idea to use this quadratic function for our objective gives us the upper bound on the curvature, which gives us a lower bound on the step size so that we are making progress. Okay, to put all of this together, here is our log barrier policy gradient approach. So at each time, at each algorithm iterate k, we are querying our system with policy pi theta k. We observe the trajectory of the system, and then we update our parameters. Okay. Using this log barrier gradient descent, where we have estimated the gradients and we have chosen carefully the step size, and we can show that with suitable choices of gamma k, eta k, the details of which are in the papers, we have safety, meaning that every policy that we query satisfies the constraints with high probability. We have convergence, so pi theta k goes to the pi theta star being the optimal policy parameter in the policy class. And we also have a sample complexity. So in order to be within epsilon of the cost of the optimal policy parameter, we need of order of epsilon to the -6 system trajectories. Okay? And you can compare this with the case where we don't have safety requirements, and you see how the sample complexity for safety is much higher. And that's perhaps the price we have to give for the safety. Okay, we're just going to look at an application. We apply this method and a test suite from OpenAI, which is called Safety Gym, and they developed this test suite to exactly test various constraint reinforcement learning algorithms. In the picture, you see an instance of this test suite where the robot is in red, and this robot is a black box to us. We don't know its dynamics. There are different options to configure it. For example, a car dynamics, or it can be a dog, or other types of dynamical system. And there is in this picture, there are obstacles that this robot has to navigate through and reach the goal set, and the obstacles can also be moving. The robot does not know the location of these obstacles, and all it has input to is camera images. So it's an end-to-end learning. And the approach is to learn a neural network parameterized by theta. So we're training the parameters of the neural network to directly learn the policy from these images. And we implemented the proposed log barrier policy gradient, and we compared it with several other benchmarks that were in Safety Gym. And I'm going to show one of the benchmarks that was the most performing at the time we tested this. And in the blue, you see the performance of the algorithm we proposed, and in the orange, you see the performance of an alternative algorithm which solves the constraint RL using the Lagrangian formulation. And this Lagrangian formulation ensures that the iterates converge to the optimal policy parameter approximately, but only at the end. During the learning and interaction with the system, there is no guarantee that iterates satisfy the constraints. And what we can observe, so let's look at just the left part behind this dashed bar. And here on the top, you see the reward. So every time the robot hits the goal set, will get a reward. And the constraint satisfaction and the Lagrangian approach in this case is faster in learning the reward. Our algorithm is much slower, but the constraint satisfaction is much better with this safe policy gradient approach. And then after the dashed bar, we applied it to a slightly different setting. So we changed the goal size to a smaller size so that it will be a little bit of a harder task for the robot. And we want to see if we can still maintain safety. And you can see that, again, we are slower in learning the rewards. It's growing very, very slowly. But in terms of safety, we are maintaining the safety much better than the Lagrangian approach. OK, so far, everything I talked about was safe learning for a single agent system. Now I'm going to talk about multi-agent learning and control. And I'm going to highlight challenges compared to single agent system and talk about multi-agent also reinforcement learning. Okay, so multi-agent systems, these are several decision makers whose objectives and constraints are coupled. For example, drivers on a road network, their travel time depends on the route choices of the other drivers. Consumers in a electricity in a power grid, their electricity bill depends on the price of electricity, which is a function of a total production and consumption of all the producers and consumers. And we can formulate this class of decision-making problems as multi-agent systems. And as a warm-up, we're going to start with static, unconstrained, and deterministic setting. Okay? So here we have n agents. Agent I in the set 1 to n has an action theta I, and the joint action bool theta is theta I, and theta negative I represents every other agent's decision. And the objective of agent I depends on her action and the action of others. That's what makes this a multi-agent system. And you can see that there is no single objective to optimize anymore, so we can't talk about an optimal solution, so we have to define a notion of solution for this problem. And we can talk about an equilibrium as a desired solution. So we say theta star is an equilibrium if every agent is doing best given actions of others fixed. So Ji of theta star I is the minimum over theta I of Ji given actions of others is theta star minus I. So agent I has no incentive to unilaterally deviate from her choice, and that's why it's called an equilibrium. Let's look at an example for cars at an intersection. So here we have two cars coming at an intersection. So both of the cars stopping is not an equilibrium because one of them could go and maximize progress. Both of them going is also not an equilibrium because they would hit each other. But one of the cars stopping and the other one going is an equilibrium. But of course, you can see that equilibria, even in simple examples, could be multiple, and they would have different values for the different agents in the system. So it's hard to talk about what is the best equilibrium. Okay, if our functions J are differentiable, then a necessary condition for being in equilibrium is that the local gradients vanish. Now, we want to look at the problem where agent I does not know Ji, but can query it. Okay, so we are in the learning setting, but it's static and there's no uncertainty, so we assume that we can measure the cost. We don't know it, but we can, for a query that we submit, we can measure the cost function. And we want to answer the question of how do agents learn an equilibrium? So we can consider the same type of approach, such as gradient descent, but each agent would now implement a local gradient descent. So she would update her parameter theta I at iteration k plus 1 as a function of theta I k minus the step size gamma k times in the direction of her local gradient, an estimate of the direction of local gradient. Okay. So a couple of challenges that I like to highlight compared to the single agent setting. First, how can agent I estimate her local gradient without knowing actions of the others? So in this case, agent I cannot use sample average estimates because she cannot fix or control the actions of the others. So the environment is changing from perspective of agent I. And she cannot also do finite differencing for the same reason. And to address this problem, one-point gradient estimators have been developed. So agent I can query her function over only at a single point, and from that single point evaluation at theta ik, estimate a gradient. But these estimators have very high variance, which makes convergence analysis and proofs challenging. And the second thing to highlight is under which conditions do we have convergence, and to appreciate the problem, if we now just consider even known gradients, if we stack together agents update rule, we get a system for all the updates. So theta at time k plus 1 is updated based on theta k minus the step size, and a stacked version of these local gradients. And what to note here is that this mapping is no longer gradient of a single function. In general, there will not exist a function j whose gradient would be these stacked gradients. Okay? It's called a pseudogradient for this reason. So only in the cases where the agent's interests align, for example, if they are cooperatively solving a problem, or if the game is so-called potential, this will be a gradient mapping. As an example, you can look at a zero-sum game. It's a very simple game where the ji is convex for each of the players. And so you look at, when you write the gradient, the stacked version of the gradients, you get this linear system. And we know that this cannot be gradient of the single function, because this matrix has to be symmetric if there existed a single function that this was gradient. What was this matrix? Okay. And this doesn't arise only in zero-sum game. It can also be in non-zero-sum game, which means that single agent analysis approaches don't generally work, because we don't have a single function whose progress we can evaluate along the trajectory of this dynamical system. So this stacked version of the gradient is called a pseudo-gradient, and we can write our pseudo-gradient descent update for agents' parameters. And over the years, there's been work on this black box learning by developing sufficient conditions on the pseudo-gradient to ensure convergence, such as a strong monotonicity of this pseudo-gradient mapping, which is an equivalent to strong convexity, but lifted to the multi-agent setting. We have also, many people, researchers in the community have also made progress in the constrained setting, where we put now, I explained everything for simplicity, unconstrained setting, but we have made progress in the constrained setting, and we have derived optimal convergence rates in this black box learning of Nash equilibria. But an open challenge is to incorporate stochasticity and dynamics in these multi-agent interactions. So let me now go into our multi-agent stochastic control formulation and highlight some of these challenges. So the multi-agent stochastic control is again, the state at time xt plus 1 is sampled from a probability transition, but this time this transition depends on the actions of all the agents. And the agent i's decision, UIT, we can think of it as a policy pi I, which is a map from the state to the actions. And boldface pi is the agent i's policy, and all the other agents pi negative I. And the agent i's cost depends on the state, which is controlled by the evolution by all the agents' actions, and the actions of the other agents. Okay. And now our goal is to compute an equilibrium policy for this multi-agent decision-making problem. In the RL, if we take the RL setting, now we want to do this by interacting with our system. And again, we would parameterize a stochastic policy. So we have a parameter for every agent's policy. And we get pi theta I, a probability distribution on the action of agent I given state at time t. And we want to find an equilibrium, the equilibrium parameters by interacting with the system, so by querying our dynamical system with these policies. And it turns out that computing or learning equilibria in this class of problems is intractable. We don't know conditions in general under which we can compute such equilibria or learn equilibria, except for very specific settings. As an example, let's look at our familiar linear quadratic setting. So in a single agent setting, if we look at policy parameterization, we parameterize our policy, linear feedback policy K with theta, and then we use a policy gradient, and here the stochasticity is from the uncertainty of the initial condition. We know that policy gradient has provable convergence in this setting. Now, when we go to the multi-agent setting and we have multiple linear quadratic objectives with a linear dynamics, in general, we do not understand under which conditions policy gradients will have convergence. Still an open problem. We also don't know in general how many equilibria we have. And there's been work on making progress for certain classes of linear quadratic problems. But for the general setting, our understanding is still partial. And this is our LQ problems are sort of our fundamental, it helps us fundamentally understand many more complex RL problems. So one way to get out of these challenges is to relax the notion of equilibrium. So we can consider an equilibrium distribution. Okay. A P star distribution is an equilibrium if given that theta is a sample from this distribution, no player has incentive to unilaterally deviate from the sample drawn here. As an example, in the traffic scenario, we can imagine that there is a traffic light which, with some probability, puts green for one side of the road and red on the other side. Okay? So it's a distribution. And the focus of the community has, over the past years, has been on learning algorithms that scale well with the number of agents, because we know this class of equilibria can be computed efficiently. Okay? But the learning problem is harder, and especially making it scalable with number of agents. So I'm going to talk about one of our approaches to address this problem in the context of multi-agent reinforcement learning, and it's a model-based approach for scalability. And the approach is that we initialize the distribution with some initial condition, and then we sample an equilibrium policy from this distribution. We submit it to our system. We play it on the system. And by interacting with the system, we get a trajectory. And from these trajectories, we estimate the transition probability kernel, from which we can estimate each player's objective function as a function of the theta. And since these equilibria can be computed efficiently, now that we have a model of these objective functions, we can compute the equilibrium distribution at the next time step. And we repeat this procedure. And we have conditions under which we have finite time convergence to an equilibrium distribution with this approach. And these conditions are based on our modeling class. So the modeling class, in our case, has to be from a so-called well-calibrated statistical model where we can have confidence bounds for the uncertainties of the model as we are learning this transition kernel. So let's just look at an application of this multi-agent reinforcement learning. So we also applied this framework to multi-agent RL in autonomous driving. So autonomous driving is by nature a multi-agent decision-making problem, and there's been test suits specifically developed for this. In particular, we used SMART, which is a multi-agent autonomous car simulation environment, and it has many instances where agents need to coordinate to do a maneuver, and it has realistic traffic data and car dynamics. And we evaluated our approach on a number of these test suits, and I'm just going to talk about one of the cases. So in this case, in the picture on the left, you see autonomous cars in red, which we are controlling, and a human-driven car in white, it's shown with a white box, whose evolution is uncertain to us. And the objective of these autonomous cars is to progress towards the goal and avoid collision. The dynamics are unknown, and this X is the position and velocity of the cars. UI, the control input of the autonomous cars, is keep lane, slow down, turn right, turn left. And the policy is parameterized by a neural network, which we use the default model that was used in this system. And so the case study shows the potential for coordination. So this agent 0 wants to change lane and come to the human-driven lane. And if both of these cars coordinate, they can both overtake the human and do this move much faster. But if they don't coordinate, they could slow down and brake more often and let the human go. And so we implement the algorithm and compare it with the single agent approach. So here in the plots, you see the single agent optima on the left and the multi-agent equilibrium. And you see the rewards, the cumulative rewards for average of the agents and for each of these agents. And what to observe is that in the multi-agent formulation, where we use the opportunity to coordinate, on the average, the agents can progress further, they break less often. So this sort of just highlights the potential of these multi-agent approaches, because driving by nature is multi-agent, and if we look at other cars as moving obstacles, where what this single agent approach is doing, we could be conservative. Good. So this brings me to summary and conclusions and outlook of the talk. So as a recap, we motivated the stochastic control as a powerful modeling framework to address the uncertainties, complexities of the dynamical system, and also the multi-agent interactions. RL provides a data-driven approach to stochastic control, but it needs performance guarantees for safe control. And we provided algorithms with proven performance guarantees for safe learning, meaning satisfying constraints during interacting with the system, and multi-agent learning when we had multiple objectives and decision makers. So there are many open theoretical challenges. For example, in the multi-agent RL work that I presented, we did not have constraints. Safe learning in a multi-agent stochastic system is a very challenging problem. You can imagine that if we have constraints that are coupling the agents, such as resource capacity constraints, such as roads or power lines, this complicates coming up with an algorithm that we can compute the equilibria. And one reason for this is that you can incorporate these constraints with a penalty, again, in the objectives, but we don't have a single objective anymore. We have multi-agents, and each of them will have different objectives. And how do you distribute the penalty for violating the constraints to all of these agents and incentivize them to satisfy the constraints? So there's a mechanism design problem that goes in there as well. Here, so far, we looked at the case where the agents, whether have or single or multi-agent, have perfect observation of a state, but a much more challenging problem is where agents have partial and asymmetric observation of the state. And our community has recognized the challenges in this partial asymmetric setting since 50 years ago, but there's only recently that we have some new tools to hopefully possibly address these with learning and other approximation procedures. And learning of good equilibria and mechanism design. So we already saw in a very simple example that we can have multiple equilibria, and each of these equilibria have different value for the different players. So how do we characterize a good equilibrium? And this can be done, for example, when we have a system-wide objective, such as in a power system, system safety and minimizing the total cost of ensuring this safety. And so in these cases, as a system engineer, we can ask how can we design mechanisms that ensure our multi-agent reinforcement learning approaches learn a good equilibria. And many more theoretical problems, but also we want to bridge the gap between theory and applications. We have a few instances of real-world problems in our lab, for example, autonomous cars, that we are trying to put these RL algorithms on them, and we can project different types of obstacles, moving obstacles, and also for interpretability of the solution, we can see the policies that come from the RL on our real-world testbed. We also have other projects jointly with robotics and architects, where we are using reinforcement learning so that robots can collaborate together and build stable structures without being given any instruction. And here you see our work in developing an RL algorithm on a simulator, very simple simulator, and then going to more advanced simulator and also having the robots to implement it. And in every step of this work, we observe some challenges, such as model mismatch, and also the fact that sample complexity of the algorithms that we come up with is quite poor for being able to solve the problem anew when we have a new instance. So these are challenges that we'd have to be addressing over the next years. Finally, an application that I did not have an opportunity in this limited time to talk to you about is the power system, which is also a passion for me because it's a multi-agent stochastic system here. So we have, in this case, the players or the agents are the participants in the power market, the consumers, producers who are submitting their bids, and they want to learn their optimal strategies to minimize the cost. And then we, as a power market operators, we can design different mechanisms to ensure that we can learn good equilibria in this system. And this is also has many open potentials that we'd be happy to talk about any of these. And with this, I would like to acknowledge the work of all my former and current PhD students. I would like to acknowledge my collaborators. I'm very fortunate to work with so many committed and kind and talented people. And I would like to acknowledge my funding. And I would like to thank you very much for your attention.
You did great. So thank you very much, Mariam. Maybe we have time for a couple of quick questions from the audience, if there are any.
Thank you for the talk. I had a question about how you approximate the utility functions for each individual player. How is that done, given, you have a cost? What do you do?
Okay, so there are two. When we start with the simpler static case, where we did in this one or the dynamic setting. In the static setting, we don't approximate the utility functions, because when we use the gradient descent, we just approximate the gradients. And we approximate the gradients using function evaluations. So imagine if you could query the function several times, then you could formulate a sample average estimate, but we make this estimation with just one query because of the issues for coordinating with agents to stay with their actions. So we just use a one-point estimation of this gradient function. And that is sufficient to, on average, get the descent direction right. But because the estimator has high variance, you will converge slowly. Yeah. Thank you.
I've seen that we have another question.
Hello. Hi.
Hi.
So congratulations on your talk. I just had a question on the first part, the single agent case. So it seems like you are running multiple iterations for the same, so over time. So it's not like the iterations are in real time, right? So you have a time horizon,
yes.
and then you're iterating multiple times.
Yes, exactly.
So then since it's not real time, why do you care about during the training phase to be satisfying the constraint?
It could be real time, so we can't, because you can implement this on the actual system, but you just have to wait to get the trajectory of length t, and then at least in this approach, or you can make shorter trajectories, but you can use shorter trajectories to estimate the functions and gradients, but your estimation error would be larger. But you're raising a good point. A different approach could be that at every time you get from xk to xk plus 1, you update your models. And this we can do. That would be a next approach we would like to explore in some sort of a Q-learning or actor critic approach, where we update the values with every step.
Okay, I'll follow up later. Thank you.
Okay.
Thank you. Is there any other question?
Yeah, thanks for the nice talk. I have a question in the second part of your talk. So in the multi-agent setting, can you comment, does it depend on how similar the agents are or how heterogeneous the agents are? Does your performance depend on that factor? And second is, what if the number of agents are very large? Are the approaches scalable or not?
Yes. It didn't. In this case, in the second, in both the static and dynamic part, it doesn't matter if they have different objectives. The dynamical system is still the same. It's influenced by action of all the agents, but they could have different objectives. So I guess that's and the policy parameterization. Of course, you can have different approaches for each agent might parameterize their policy in a different way. That's the kind of difference the formulation accounts for. Of course, you can cast problems where you have multi-agent systems with independent dynamics and different heterogeneous dynamics as an instance of the problem we pose by just stacking together the states. Okay, so we can have that the agents are independent, they have heterogeneous dynamics, but you will kind of put everything together and you get a stochastic system whose evolution is controlled by all the agents. In the second part, can you please repeat the question? Yeah, it's a good question. Scalability is one of the main challenges in the multi-agent stochastic control and reinforcement learning. So for our instance, the reason we use a model-based approach was exactly to address this scalability, because we are making some simplifications. We have some coordinator that is estimating these models. If each of the agents wanted to make a local estimate of the model, then it would make the problem much harder because you have to coordinate that estimation error, and convergence could be much slower. But we are in the finite n region, and there's a lot of excellent work on mean field approaches where n gets large. And especially recently in this conference, I learned, for example, that you can use these mean field approaches to approximately solve this problem of partial and asymmetric observation by just looking at a mean field formulation. But so that's a good question, and there you have to bound your approximation error to the finite n case. Yeah. Thank you.
Thank you very much. So, okay, last question, but really, I mean, that's the last one. Can you please?
Fantastic talk, and congratulations on the award as well. I just wanted to ask about, in the first setting with the safety constraints, the safety constraint is represented as an expected value of a cumulative
Yes, that's a good
function,
question.
right?
Exactly. So I have a slide about this. So the constraint RL formulation. So we can have, as I mentioned, a finite horizon. It's a good and important question, so I wanted to talk about it if somebody is interested. In a finite horizon setting, you can encode probability of trajectory staying inside a safe set using this formulation by using indicator functions of the set. Okay, and introducing some state augmentation, but you can recast the safety probability for a trajectory or reachability and so on. You can encode it with a slightly modified stochastic control problem with this additive cost. In the infinite horizon setting, for making sure this sum is bounded, we usually introduce a discount factor, okay? And so far, our results are for the discounted setting. The approach, the log barrier approach, can be extended, and that's what we're doing next. But the theorems we have is now for the discounted setting. And I would like to actually, I find the first case more important because it has a direct meaning in terms of probability of safety. And there's works that also show approximate gradient dominance in this finite horizon setting. But you have to take a time-varying policy now, so you have policy parameters for every time step. So the analysis is a little bit more detailed, but the approach could be extended. Thank you for this question.
Thank you. So, as a conclusion of this beautiful talk, I would like to give Mariam the plaque associated with the award.
Thank you. Thank you very much. Thank you.
Congratulations. Thank you very much, Mariam.
Thank you. I'd just like to thank you once again for all of you for your attention, and thank you for choosing me. And it's been a pleasure to be in this community, and yeah, it's an honor to receive this award. Thank you.
Thank you so much, Mariam.
You're welcome.
So.